All right, so so far we've talked about sp3 hybrids. That's when you have uh, you've got your s orbital and then your 3p orbitals, and you combine them all together, and then you get 1, 2, 3, 4 new sp3 orbitals. This is sp3 hybridization. This is useful when you have 4 charge clouds to accommodate in whatever the molecular geometry might be. We did that with a couple different examples. We did it both with methane and then we did it with PCl3. Both of those had 4 charge clouds. Methane had 4 bonds, PCl3 had 3 bonds, but the hybridization remains the same. Of course, sp3 hybridization isn't the only type of hybridization. It depends on how many charge clouds you're trying to accommodate. So what happens if you've got 3 charge clouds to accommodate? In that case, you don't need to hybridize all 4 of those. You just need 3 good solid equivalent degenerate orbitals. And in order to do that, we can take our trusty energy diagram of s and p orbitals. Doesn't matter if they're 1s, 2s, 3s, whatever. The hybridization is the same. And we can hybridize. In this case, we're only going to hybridize these 3, in which case we're going to be left with an sp3, or I'm sorry, not sp3. We're going to be left with 3 new orbitals that are all sp2 hybridized, and then we're going to be left with the original p orbital that is unhybridized here. So we've got the unhybridized p atomic orbital on whatever that central atom is. And so the sort of final, so this is to accommodate 3 charge clouds, and we'll do an example of this, and I'll just show you off the bat then. The last type of hybridization would be if you've got S and P and you're trying to accommodate 2 charge clouds, then you only need 2 hybrid degenerate orbitals, in which case you're going to hybridize just 2 of these like this, and that's going to give you 2p orbitals, so 2p unhybridized, and then you'll have 2 what we call sp hybrids. Remember, the naming convention here for hybrid orbitals, in this case the sp2, comes from the fact that in order to get 3 new sp2s, we've got 3 of these here, we had to hybridize 3 atomic orbitals, 1 of which was an s, and then 2 of which were a p. So the naming convention just comes from how many, the quantity of individual atomic orbitals that you combined. Sp is the same. So in order to get these 2 new sp hybrids, we had to take 1 each from the s and the p. And so there's 1 each that combined to form these. So what does this sp2 hybridization process look like from the atomic orbitals perspective? So remember again, the energy diagram looks like the one over here on the left. So we've got our trusty 2s and 2p atomic orbitals. They're always going to look like this. But when we have 3 charge clouds to accommodate, then we need 3 degenerate orbitals. We only need 3 of the 4 here, so we're only going to take 3. And we're going to smash them together, average them up, and we're going to end up with 3 new sp2 orbitals. Those are the ones in green. We're going to be left with 1 unhybridized p orbital. It's the same as it was before. Nothing changed. So what does that look like? Well, here we've got the picture to the right, the same picture as we had before, where we've got our 3 p orbitals. So we've got 2p z, 2p x, and 2p y. We've got our 2s. So these are the same 4 orbitals that I'm representing in the energy diagram. But I'm only going to smash 3 of these things together. So I'm only going to combine, say, these 3. And then this one is going to remain unchanged or unhybridized. And so these things will hybridize in this way. So literally mathematically, we're just taking these probability functions and doing a linear combination of their functions. So what we get are 3 new equivalent orbitals that look like this. So they look very similar to the sp3 orbital. Remember, the sp3 orbital was a little bit different. It was still had two lobes, but one lobe was a lot bigger. Here, this other lobe is not quite as pronounced in difference in size, and that makes sense because we're negating the addition of one of our p orbitals. So we get 3 of these new sp2 orbitals. Those are all going to orient themselves in this sort of plane in the center, like this. So all 3 are going to point like this, away from each other in sort of a triangular shape in this plane, like this. And then you'll have the p orbital that remains unhybridized pointing into and out of the plane, pointing here and here. Okay, so this is the geometry for an sp2 hybrid orbital. Let's do an example. So let's start with this example of ethylene gas. This is the stuff that makes fruit ripen. This is sort of the rotten banana smell. C2H4. I'm not gonna walk through every detail to draw this Lewis structure because you know how to do this pretty well now. But this is the Lewis structure that we're starting with. So let's identify how many charge clouds we have around each of these carbon atoms. So this carbon atom we have 1, 2, 3, and this other carbon atom we have 1, 2, 3. So each of the carbon atoms has 3 charge clouds. Remember, 3 charge clouds necessitates the use of 3 degenerate orbitals, 3 orbitals that have exactly the same energy and shape and size, which means we need sp2 hybridization. So when we have 3 charge clouds or trigonal planar centers, then we need the sp2 orbital. So let's draw what this might look like, and it's going to be interesting because we've got this double bond, so that's going to have some cool implications here in a second. So let's draw up first the 2 carbon atoms in the center, and let's then draw the 3 sp2 orbitals that are all going to be 120 degrees relative to each other. So we know there's going to be one big old sp2 orbital here with a little tail, and then there's going to be one big old sp2 orbital here with a little tail. That's going to form this one single bond overlap to begin with. And then we know that there's going to be one sp2 there, and another sp2 there, one sp2 there, and one sp2 there. So red here denotes sp2. We've got 3 sp2s on each of these carbon atoms. But remember that in order to make sp2 orbitals, that means we're leaving out one of our 2p orbitals, right? We're only hybridizing those 3 to get to 1, 2, 3 of the sp2s, and then we still have a p orbital. So that means each of these carbon atoms still has a p orbital, and that p orbital is pointing into, and we'll say that's sort of dotted there, and out of the plane. And maybe I'll draw it this way here just so that you can see them both. Those black orbitals are the 2p orbital that remains unhybridized in the energy diagram here. So remember, carbon has 4 valence electrons on it. So it would have had 1, 2, 3, 4 to start with, which would have translated to 1, 2, 3, 4 in the hybrid energy state. That means that there's going to be 1 lone electron in each of the sp2 orbitals, but there's also going to be 1 hanging out in the p orbital. Okay, so right off the bat, we've got the electrons right here in this sp2 that overlap. That forms that nice single bond between the carbon. We've got an electron hanging out in that orbital, electron there, electron there, and electron there. But then each of the carbon atoms has its own electron hanging out in its respective unhybridized p orbital. So we're not quite there yet because we haven't described this second bond yet. Okay, so I just redrew 1/2 of each of these black p orbitals with the blue half just to show that p orbitals, remember, have 2 phases, and phases have to overlap identically in order to form that bond. And so the actual second bond forms through the overlap of these 2 p orbitals on the side. So these things are pointing into and out of the plane, and they side-on overlap right here to form this second bond here. So the first bond comes from the head-on overlap between the sp2 orbitals of the carbon, and then the second bond comes from the side-on. We'll write this as head-on. The second bond comes from the side-on overlap of the p orbitals of the carbon. Those are the two bonds, and they actually get two different types of names depending on whether it's a head-on or a side-on. So a head-on bond we're going to call sigma. Those are strongest. So that's a strong bond because they have the most overlap. Big overlap because you've got a head-on overlap there. These side-on overlaps are a little bit weaker just because there's less volume, and we call these pi bonds. So when you have a double bonded structure like this is always going to be the case. One of the bonds is going to be head-on overlap between a hybrid orbital. We're going to call that a sigma bond, and the other one's going to be a side-on overlap between two errant p orbitals, and we're going to call that a pi bond. That constitutes the two bonds in space. Again, I draw this out to sort of show you the step-by-step, but then I'm going to paste on an actual picture of what this molecule would look like, and so hopefully you can see that a little bit better here. Alright, this is the same molecule, and so you can see these are on the left side, these are the two carbon central atoms. I don't know why that did that. The two central carbon atoms are here, so those are like that. The green represents the sp2 orbitals. They're showing them in these axes that are a little bit easier to see. So remember, those three sp2 orbitals are all identical. They're all 120 degrees relative to each other. And then you've got that unhybridized p orbital that's sticking up and down in the plane, and the red and blue denote the two phases of that orbital. It's the same orbital, but the phases have to be the same to overlap. And as we'd mentioned before, you've got your 2s and 2p energies of orbitals, and for the carbon, those all had one electron in them, and when we hybridize 3, what you get are 3 new sp2 orbitals and the original p orbital, and now you've got an electron in each, and that's reflected in these pictures, right? You've got one black dot in each of the green lobes of each of the carbon atoms, but then you also have one black dot in each of those p orbitals that are unhybridized. So if you bring these two things together now, and we allow these to overlap, what you'll see is the double bond, the single bond will form first based on the head-on overlap of these two sp2 orbitals. So that becomes sp2 sp2 overlap, and we call that a sigma bond because it's head-on. And then the side-on overlap of those red phase of the p orbitals, that gives us that pi bond or side-on overlap, and that's a p type bond between these two carbons. I haven't shown this explicitly, but remember we are making the molecule ethylene, and it looks like this. So then of course on each one of these we have then another hydrogen atom that comes in, and it shares its one electron to form this ultimate final structure. So this is what we'd be looking at here. So once you get some practice, you can just take a look at a molecular structure, and once you identify its molecular shape, you can immediately assign what type of hybridization is required to define that particular bonding center. And so if we look at this molecule, this is propylene. This is a more complicated molecule than you're used to looking at. So let's break it down into the different carbon centers, and let's think about what type of hybridization would be required for each of these centers. So if we look at the carbon here, you can see that it's got 1, 2, 3, 4 bonds, 4 charge clouds. That means it's got to have an sp3 type tetrahedral hybridization. That's all we need to know. That's simple as that. 4 charge clouds will always have an sp3 type hybridization. If we jump over to this carbon here, we've got, we'll do this in green, we've got 1, 2, 3 clouds. 3 clouds in this case is going to require sp2 hybridization and a trigonal planar type geometry. The same is going to be true for the carbon on the right, where we have 1, 2, and 3 again. So it's pretty quick once you get used to it. If you have 4 charge clouds, sp3. If you've got 3 charge clouds, that's an sp2 type hybridization. Alright, so I'd already alluded to this a few minutes ago, but the last type of hybridization that we can have is just sp, where we're taking one s orbital, one p orbital, and we're smashing those together, and then we're leaving all the other atomic orbitals untouched. So the scenario in which that would be useful is when you have 2 charge clouds on a particular bonding center or central atom. Then we need the sp type hybridization. So this general table here is what you're going to want to remember. 4 charge clouds, we need all the 4 orbitals that come with sp3, 4 hybrids. For 3 charge clouds, we need the 3 hybrid orbitals that come with the 3 sp2s. For 2 charge clouds, we just need 2 hybrid orbitals that come from the 2 sp type hybrid orbitals. So again, in terms of energy here, if this is the energy axis, hybridization of just an S and a P would be to just take these 2 and then leave these unhybridized. So what we'd be left with are 2 hybrid sp orbitals and then 2 non-hybrid or unhybridized p orbitals. So just like in the sp2 example that we did before, we had 1 p orbital that was unhybridized. Now we've got 2 of them. We only needed 1 to make that second sp hybrid orbital. So what does that look like? Well, if you take an s orbital that looks like this, and then you add it to a p orbital that looks like this, you're going to get 2 orbitals that look pretty similar to the original p orbital. And so how do those look like on that, that original atom? Well, you've only got that sp orbital, the 2 sp orbitals, one here and one here, and then you've got your 2 unhybridized p orbitals that are shown in the red and the blue in this case. Alright, a common example of a molecule that would require sp hybridization would be this thing called acetylene. So again, the requirement for sp hybridization is that you've got a atom where you've only got 2 bonding center or 2 charge clouds. So we've got 1, 2, and the same is true on the symmetrical carbon over here. We've got 1, 2. So both of these carbons that are bound to each other are going to be bound through an sp hybrid. And sp hybridization is really common when you've got a triple bond like this, because we need those extra p orbitals that are poking out to form those side-on overlaps, those pi bonds like we had in the ethylene case just a few minutes prior. So what does that look like? Again, I'm going to draw it and then I'll paste on an actual digital version so that you can see. Okay, so I've got the 2 carbon atoms represented here and what their hybrid orbitals would look like. So carbon on the left, carbon on the right, and these 2 would be then coming together to form this new bond. You can see I've got the 2 sp orbitals. If we look just at the left carbon, each one of these green lobes is one of the sps. One is pointing towards, one is pointing back. Don't be confused. It looks like it could be a p orbital because it looks really similar, but a p orbital would have 2 phases, whereas this this sp orbital actually just has this one phase like this. So then we have the p orbital poking up and down on this vertical axis. This might be a y-axis here, this might be an x-axis, and then z might be going sort of out and in. So then we also have the pz that's aligned with that z-axis. Exactly the same setup over here for the other carbon. Remember, I always draw up the energy diagram because it's really helpful to think about this. If we have our S, well, it's 2s and 2p for carbon to start with, those would have 4 valence electrons in it. That would hybridize, and in this case we would have 2 of the p orbitals, and then we'd have 2 of the sp orbitals, and we'd have an electron in each of those. So in that case, each one of these orbitals up here is going to get its own electron to hang on to. So I'm going to put one purple in each. So there's a purple electron there, purple electron here, purple there, and a purple there. The same is going to be true on the other carbon atom because it has the same number of valence electrons. So now when we bring these two things together, every one of these unpaired electrons is going to pair up in space to form those new bonds. Alright, so after 3 minutes of drawing here, I got this structure that looks like that's the combination of these two carbon atoms, and let's make sure that it all makes sense. So first off, the two sp orbitals are first going to come together and make this nice head-on overlap. That's that big green mass right in the center, and that is going to be our that's going to be our first bond in the triple bond, and that is our sigma head-on overlap that forms between the sp and the sp on that carbon. Okay, so then we have second, we have the side-on overlap that forms between the two p orbitals that are pointing up in the y direction, and that's what this big red mass is at the top. So that's a side-on overlap. Here are the two purple electrons that are being shared there. That's pi, and that's going to be a pp type interaction. The blue down here doesn't have any shared electrons in it because it's all the same orbital, right? So the electrons are here and they're here simultaneously in this orbital. And then last is the hardest one to see, but that's that p orbital that on the left here is the dashed line that's pointing into and out of the screen, and I tried to draw it into and out of the screen here, but there's these two purple electrons that are also there, and that's this last pi bond, and that's also a p bond. And so between the carbon atoms in acetylene, you have one bond that is from, let's say, let's draw it green. That bond is coming from the sigma, and then you have two bonds actually that are coming from pi bonds that are side-on overlap, and that gives you that overall structure. Obviously excluded from here are then the hydrogens, but those are pretty easy to draw. So then we'd have hydrogens come in with their 1s orbitals, and they would grab and share these electrons out here with their 1s1 orbital, and this would be the final structure. So let me show you the digital version of this. So not so far off. The digital version looks pretty similar. We've got the two carbon atoms to begin with, so there's carbon and there's carbon. These two things are going to be added together. We've got our two sps, the two green lobes, on each of the carbon atoms, and then we've got the two p orbitals that are unhybridized. Those are going to come together. We're going to get that sigma overlap, the head-on overlap right at the beginning, or right in between the carbon atoms. Then we're going to get this pi bond here, and then we're going to get that pi bond back over there, and that's going to form our acetylene.